And welcome to the video. And in previous video, we saw the delay causing ringing and as well as introducing the potential instability. And in this video, we will see negative feedback system with delay and let's see the tolerable values for delay. So we have a negative feedback system and we can, to analyze the delay in it, we can set a component of delay with a value of td in our negative feedback system, and we will write the differential equation for the system and then solve for the value of v naught. But before that, let's see if we introduce a delay over here, then the feedback voltage, which is basically v naught by k, this is k naught t. So feedback voltage, which is v naught by k, and v naught is a function of t. After coming at this point, it will be v naught as a function of t minus the delay amount by k. So let's say we realize the voltage function as a function of time, and as output, the if we consider v naught of t as output, so at the input of the integrator will be nothing but this value 1 by omega u times dv naught by dt. And we know from this difference maker, our input VE of the integrator is nothing but VI minus V feedback, and we have the value of feedback. So putting all the values together, we will arrive at this equation. And previously, when we solved for the system without delay, we assumed a step input and output initially at 0, and then apply step, and we saw what happened to the output. So for simplicity, let's assume the exact opposite case for now. And let's say that we have our VI as a constant step at 1 volt. And we'll assume that the output V naught is at already at a steady state of voltage k times the V in, and as V in is 1 volt, so basically the output is at k volts. So we will know that as per v naught by k comes out to be k by k, which is equals to 1. So at this point, we'll get a voltage of 1 volt, and thus the input over here is basically 1 volt minus 1 volt, which is 0. So this is before, like, we start analyzing. So this is a steady state before we start analyzing, and the moment we start analyzing, we will consider it as t equals to 0. And now let's say at t equals to 0, we will apply steps to 0 volts. So initially we had 1 volt. Now at t equals to 0, we step down the voltage and then analyze the output voltage. So as Vi comes out to be 0, then this Vi will get rid of this Vi from this equation, and this equation can be written like this. And as we can talk over here, let's discuss what happens to the negative feedback in very layman terms. So when we step down, the output voltage will not change instantaneously. So at t equals to 0, it will be at potential k, and this point will be at potential voltage 1 volt, and thus our feedback will also be at 1 volts. So without the delay, the equation could have been like this, and which we solved in previous video. So when we take vi as 0, this would have been our equation. So firstly, let's take a case without delay. So this is the case without delay with v in as 0. So from this equation, we can write this way, and where this factor is called as a scaling factor, and the solution of the differential equation will remain the same whether we will have a scaling factor or not, because it's a linear differential equation and that's how it behaves. So basically over here we are saying that we have a scaling factor, and the equation is saying that the time derivative of v naught is the same as the function of v naught itself. and along with a scaling factor, obviously. So the solution to such form of equation, as we learned in our class 12th mathematics, is basically exponential of t, and along with it we have our scaling factor parameters. So now in case of delay, we have this equation where this there is a delay factor. So we can again rearrange the equation in this form where we have our scaling factor, and again solution to this exponential solution to this equation is again an exponential. So basically it is exponential of t times exponential of minus td along with the scaling factor parameters. So now we will plug the exponential into this equation and see the parameters of the exponential required in order to satisfy the equation. For that, we will assume b naught t as an exponential, as we saw that the solution to this equation is basically an exponential. So we will take v naught t as vp, some amplitude, times exponential of sigma t, and writing an equation by putting the values of value of v naught t into this, we will get some sort of equation like this, and this we can rewrite like this. And when we rewrite like this, our vp cancels out with vp, and our exponential of sigma t cancels out with exponential of sigma t, and this is nothing but we had a dv naught by dt over here, right? And we decided to replace the value of v naught by this value. So this is our v naught, and we take the derivative with respect to time. So this value comes out to be this value. So this is how we are representing dv naught by dt at v naught equals to vp exponential of sigma t. So from this equation, we arrive to this kind of result, and this cannot be solved explicitly, but we can look at the function and try to solve for sigma numerically. So we have this equation like this, where this k goes down over here, and we have equation in this format, and this particular value can be rewritten as this entity and this entity over here and over here, and we will multiply and divide by the factor of omega u by k. Why? Because omega u by k is our time constant of the system, and we'll sooner realize that this makes the evaluation or analysis easy. So by redefining the variables, we can redefine them like this. And let's say sigma, so we have exponential of sigma and td with a minus sign. So as we have time, so we know that sigma has the dimensions of frequency, as it all club together in an exponential. So what we do is we normalize sigma by frequency again in order for achieving simplicity. So this is how our equation will look like. And now in this equation, we will define sigma by omega u by k as sigma prime, and we will define this entity, which is basically this entity, as normalized time delay tau. So then our equation comes out to be like this, where we have sigma prime plus exponential of minus of sigma prime into tau equals to 0. So now we will be known with the values of time delay td, omega u, we have the value of k, thus we know the value of tau, and we have to solve for sigma. So basically sigma is nothing but denormalized value of sigma prime. So again, we have the value of omega u by k. So if we have sigma prime, then basically we have our sigma. So for tau equals to 0, for like tau equals to 0, meaning that td equals to 0, or basically ideal case where there is no time delay, sigma prime comes out to be -1, and thus sigma comes out to be -1 divided by k by omega u, basically minus omega u by k. So this is what gives us the sanity check. And now we have our function, which is the function of sigma prime, which can be represented as a function of sigma prime And to plot this function, it cannot be plotted or find, we cannot find the value of sigma prime explicitly. So we will plot a function for sigma prime, and let's divide it into two different functions, f1 and f2. So basically sigma prime is made up of f1 and f2 over here, where f1 is basically sigma prime and f2 is exponential function. So when we plot our function of, like, when we plot our f1, so this is how our f1 will look like, which will pass through origin. And when we plot our exponential, or when we plot our f2, so f2 is depending on the value of sigma prime itself, and as well as f2 is depending on the value of tau. So this tau is very important because f2 will somewhat look like very steeper, and this kind of a curve which asymptotically goes to sigma prime. And this curve is for the very large values of tau, and for the very small values of tau, this curve will look like this. So basically what we have is, we have our function 1 and we have our function 2, which is dependent on tau. So we will when we club these two functions, so we can say that our f2 depends upon the value of tau, and when sigma prime is equals to 0, our f2 becomes 1. So basically that's the value. So when our sigma prime equals to 0, our function basically becomes 1. So for the smaller values of tau, and let's say for positive values of sigma prime, our function will basically look like this, which will reach to f1 asymptotically. So we can say that for smaller values of tau and for positive values of sigma prime, very large values of sigma prime, the exponential will tend towards 0, and the curve of our function approaches to the curve of f1, which is for positive values of sigma prime. And for smaller value of tau and for negative values of sigma prime, the curve basically goes to 0. But for a very large effect due to tau, it again bounces back, and for very large value of negative values of sigma prime, the exponential takes over and it again bounces back. So basically over here we are getting the roots of function of sigma prime, and both roots will occur below the value of -1, or the larger negative values than -1. And similarly, talking about the positive side, so for the larger value of tau and for positive values of sigma prime, the function quickly approaches f1, and for larger values of tau and negative values of sigma prime, the function does comes below, but then the exponential is rising so fast that the function goes up again without even touching the 0 line. So there will be a value. So basically these curves totally depend on the value of tau, and there will be a value of tau for which the function has two same solutions. So basically the minimum value of the function will be touching the x-axis, or will be equals to 0. So this condition is very crucial and we'll talk about it soon. So we have a negative feedback amplifier with delay, and we realize our v naught like this. So we have this equation or a function where tau is nothing but td divided by k by omega u, which is a known value, and sigma prime is basically a normalized value of sigma. So this equation has two solutions, sigma prime 1 and sigma prime 2. So basically we have sigma 1 and sigma 2 when denormalized. For the smaller value of taus, so basically when the value of tau is smaller, this is how our curve will look like, which will give us the solutions, two solutions, sigma 1 and sigma 2. But for the larger values of tau, our curve will not touch or cross the x-axis, so we will not be having solutions, or basically we will not have real solutions. Then we have to jump for the complex plane. So, but that's a different part, and we'll discuss it later. So the function is equals to 0 will give us the boundary to tau, where we will either have a solution or no solutions. So basically, talking about the two solutions for the smaller values of tau. So having two solutions, sigma 1 and sigma 2, means we have exponential sigma 1 t and exponential sigma 2 t as our solutions, and which is a solution to our differential equation, which we represented by this equation. And to complete the solution, we'll be like completing the solution to v naught of t as a1 exponential sigma 1 t plus a2 exponential sigma 2 t, and a1 and a2 can be determined from the initial conditions. So what initial conditions are we talking about? So let's say we have a negative feedback loop with a time delay of td, and this we discussed how it arrived. So let's say we have a steady state input of 1 volts up to time t naught equals to 0, and at t equals to 0, we step down the voltage, the input voltage. So what happens to the output voltage? So up to t equals to 0, v naught is at a steady state with the value of k, and when vi falls to 0 due to the delay, the input to the integrator changes from 0 volts to minus 1 volts, but the value of output will start to drop, but due to the delay, the feedback will still be at 1 volt. So due to the delay, the feedback will still be at 1 volt, and thus the input to the integrator will still be at minus 1. So meaning that VE will still be at minus 1 for the delay of time TD. So this is a delay of time TD, and for that time, our VE, even though our input voltage has dropped, but it is still at 1 volts. So basically, VE at minus 1 volts till TD means the V naught will decrease with a slope of omega u until the time t equals to TD is reached, and after TD, V feedback starts to reduce, and thus the as V feedback starts to reduce and this falls to 0, so VE starts to increase, resulting in the slope like resulting in slope of our V naught start to reduce, and it finally reach 0 asymptotically. So now these two initial conditions, so basically these two initial conditions will give us the values of a1 and a2. How? So basically at t equals to td, our v naught comes out to be k minus omega u times td. So basically the decrease in k starting from here, starting from t equals to 0 to t equals to td, is basically nothing but omega u times td, and thus our v out will be k minus omega u times td, and the slope will be minus omega u, and slope is determined by dv naught of td divided by dt. So basically we talked about these two values, and thus we have two equations and two unknowns, and hence from here we can find the values of a1 and a2. So basically the solution is v naught t equals to, as we discussed, a1 exponential of sigma 1 t plus a2 exponential of sigma 2 t. I forgot to write the exponential over here. So v naught of v naught at time of td is nothing but k minus omega u td, and this is what we got over here. And by rewriting this equation, we can simply say that v naught at td is k times 1 minus tau, or we can simply say that at t equals to td, dv naught by dt equals to minus of omega u. So we have these two equations from here, and thus we can find the plot of the function of sigma prime versus sigma using the Python, and we will get two solutions, sigma 1 and sigma 2, and the solution will be basically putting the values of sigma 1 and 2 and normalizing it with omega by k times t. So basically what am I talking about? So we have a Python plot where we have plotted the function of uh, sigma prime versus sigma prime, and we have different values of taus. So this, at this point, this is the point where, like, this is our x-axis and this is our y-axis, and this point is basically where the value of function is 1. And from this point, for the negative values of sigma prime, depending upon the value of tau, we have either we have, like, for very higher values of taus, the curve is not coming to x-axis, but for very lower values of tau, we are having such kind of curves, which basically, when goes further, so basically this is our x-axis, so cuts the x-axis two times and gives us the real solutions. So basically over here, if we see that this point and the point very close to this, these two are giving us the values of sigma 1 and sigma 2, and when we put these values in our um, solutions, so basically we will get our two solutions to our equations. We can find the values of a1 and a2 by boundary conditions, and hence we can find the v naught of t, and that's how we solve for v naught of t when we have a delay. So now the value of tau for which the curve of function of sigma prime just touches the x-axis can be found by differentiating the function by sigma prime itself and then equating it to 0. So basically we are saying that the minimum value of curve should be equals to 0, and basically that will give us the boundary condition for which we are getting real values of solutions for the minimum values of tau. So when we plot the transient response of v naught t versus t, it turns out that there is no overshoot for tau equals to 0, 0 0.1, 0 0.2, or 0 0.3. And basically we saw the curves for the exact same values, and also the v naught reaches faster to steady state than the that of having td equals to 0 or 0 delay, and the fastest response is at tau equals to 0.3675, and this is the largest value of tau for which there is a solution. And how did we arrive at this value? So basically from here, when we differentiate our function with respect to sigma prime, we will get this value, and when we equate it to 0, and then when we solve for it, so we will get sigma prime as log of tau divided by tau, and for this value of sigma prime we get the maximum of the function as 0, or the minimum of the function as 0, not maximum. And when we substitute this value of sigma prime into our main equation, then we will arrive to such kind of equation where when we solve for it, so basically our tau comes out to be 1 by e, whose value is 0.3675. So for tau greater than 1 by e, we have no real solution, but this is how we can set the boundary condition of tau, and at this value of tau, we will be getting the highest or the fastest transient response, and our system will reach to its steady state fastest by having the tau equals to 1 by e. And I think we have discussed everything about the small time delays introduced to a system, and in the next video we'll talk about the large delays introduced to negative feedback system. That's all for this video. Thank you for watching.